Okay, we're going to talk about nuclear magnetic resonance spectroscopy, and in particular, what we're going to focus on, and we should probably put this in here, is proton. Okay, because that's what we're going to focus on, is actually the hydrogens, okay, as opposed to a carbon. All right, so in theory, NMR, nuclear magnetic resonance spectroscopy, is a technique which is based on the absorption of electromagnetic radiation in the radio frequency of the spectrum by the nuclei of atoms. Okay, it's based on the property that spinning charged particles generate a magnetic field. Nuclei of atoms behaved like tiny little magnets, all right? When there is no electronic field, they're all kind of randomly spinning. When they're exposed to a magnetic field, okay, they line up in the direction of that magnetic field. When they returned to the original kind of random state, they emit the energy that they absorbed in the radio frequency region of the electromagnetic spectrum. And then this emission gives the signal for the nuclei, or the peak, on the NMR spectrum. Different nuclei are going to emit radiation at different frequencies depending on the types of atoms that they are attached to. So depending on the type of what we will soon find out is called their chemical environment. Okay. So for example, we have these three molecules. Let me get the pen working. Okay. All of these hydrogens are in the same chemical environment, and they will absorb and have the same peak or signal. These hydrogens are all in a chemical environment, the same but different than this one. The presence of this chlorine is going to make these hydrogens, or protons, absorb in a different region of the NMR spectrum. If I add yet another chlorine, it makes these hydrogens in yet a different chemical environment, the same one between the two, but different than these three, different than these four, and it's going to change the frequency of the electromagnetic radiation that they absorb. Okay. Now, there's going to be really four things that we look at when we look at a NMR spectrum. The number of peaks on the signal, okay, or signals, okay, is going to be the number of chemically unique hydrogens in the molecule, right? So it's going to be really the number of chemical environments. Spell environments, right? That's supposed to have an N in there. All right. The types of H's are going to be present, and that's going to be the location of the peaks, also called the chemical shift. And we're going to look at these in more detail, look at two of these first, and then pull the other two in a little later. Then the number of each chemically unique hydrogen is going to be the integration, or the area under the curve. In here, we're going to see we're going to need a little diagram on the graph, or they'll actually give us numbers. Okay, and that's what we're going to look for, but that's going to tell us the ratio of hydrogens in each of those chemical environments. Then the last thing, and the fourth thing, that the NMR spectrum is the number of H's near to each other, and this is called spin-spin splitting. This is only in high resolution NMR, and we'll see what it looks like when we get there. So take a minute, pause the screencast, and see if you can say how many signals or peaks in the Hnmr spectrum, meaning how many for each of these three molecules, how many unique chemical environments will they have? Okay, hopefully you took a moment to think about it. Okay, these four are going to have one chemical environment. This will have one peak. We're looking at these hydrogens and these hydrogens. If I look at any of these hydrogens, they're connected to a carbon, and three H's. Well, this hydrogen is carbon, carbon, three H's. This is actually the same chemical environment. I will only see one peak. Okay. Looking at this, I have these H's, these H's. Hopefully you can tell that these three are same chemical environment, these three are same chemical environment. Looking at this one, I have a carbon-carbon double bonded O carbon. Looking at a hydrogen in this environment, carbon-carbon double bonded O carbon. Okay, this again is just one peak, one chemical environment. Now take a moment and look at these molecules. Pause, make sure you have an answer. Okay. This one I have these hydrogens are one environment. These are another. I will have two peaks. I have this hydrogen. These hydrogens, I'm going to have two peaks. And then if we look at, remember each one of these is a carbon and a hydrogen connected. And then remember, you also have that resonance. This is one peak. All of these hydrogens are in one chemical environment. Okay. So just to show you what you're looking for if you actually see the NMR, this is what the NMR spectrum will look like, right? All of these hydrogens are in the same chemical environment, and I only see this one spike. If we look at this, remember I had these hydrogens were one chemical environment, and these were the second chemical environment. This counts as one peak, and this counts as one peak. All right, so those are the two peaks. Okay, now if you notice, these two peaks, okay, they're on this scale, parts per million, and they're on the scale. The location of this peak is going to be important. Right, that's what we're going to talk about next. Where the peak or signal is located is called the chemical shift. It's measured in parts per million. It's called the delta scale, and it is always, or it's in reference to tetramethylsilane, TMS. If you look at this molecule, it has 12 hydrogens that are all chemically in the same environment. What happens is they set this TMS equal to a chemical shift of 0, and everything else then is relative to this TMS. So this scale runs from right to left and is called the chemical shift. Peaks to the left of TMS, which are all of them, are said to be downfield of the TMS. Factors that are going to affect the chemical shift. The more electronegative elements tend to de-shield a proton because they pull the electron cloud to themselves, and they cause the chemical shift to be more downfield or at a higher number, so they cause the peak to move farther downfield. The farther away the hydrogen gets from that electronegative element, the more that de-shielding effect decreases. Adding more electronegative atoms are going to cause an increase in that chemical shift. Okay, so if we go back and look at the chlorine substituting on a methane, you can see with one chlorine the chemical shift is a 3.05. I add 2, it shifts farther downfield to a 5.3, and then I shift farther down with another chlorine added to a 7.27. But remember, all of these hydrogens are still in just one chemical environment, so I will only see a single peak. Looking at methyl ethanoate, it has two types of hydrogens. Here's one chemical environment, here's another. Oh dear. Okay. So we see the one, this is, I don't know if you can see it very well, this is one peak, here's the other peak. Okay. So how can we tell where they're going to be? Well, their chemical shift, there's the table in your data booklet, table either 26, 27, or 28. And it shows you approximately what that chemical shift will be, where those peaks are going to be found. And that's going to help us identify what functional groups are present in our molecule. Okay. And we'll get practice in class doing that. So the number of protons in each peak, this is where we're going to look at the area under each peak. The area under the peak is going to be proportional to the number of protons in that chemical shift, or at that chemical shift in that chemical environment. This area has to be shown by an integral trace. Okay, so it's going to be like a dashed line that we see, okay, or they actually write numbers. Okay, and it gives us the ratio of the hydrogens in one chemical environment to the hydrogens in the other. The height of that integral trace can be compared to give that ratio. All right, so for instance, if we look at this particular NMR, we have these two peaks. Here, this distance here, the height of this distance, because this is your integral trace line, okay? The height of these two things compared to each other is going to give us the ratio of the hydrogens in each chemical environment. Okay. So if we look at this chemical trace, we would be able to measure this height with a ruler, compare it to this height, and we would see that it's a 1:3 ratio. So it tells us that those hydrogens are, for every one of these, I've got 3 in that other environment. Okay, and here's an example where it shows you the numbers instead of having to measure with a ruler the area underneath them. Okay. So if we look at this NMR, I have 1, 2, 3, 4 peaks. So I know I have 4 different chemical environments. Looking at the ratio of the integrations, 1 to 2 to 3 to 6. Okay. And then your chemical shift is going to give you some idea of how they are, what they're connected to. Now let's talk about spin-spin splitting. This is the effect that a proton on an adjacent carbon has on each other's magnetic field. What you look for is a hydrogen that is within 3 bonds to another hydrogen. And these hydrogens are going to affect other hydrogens. And what they do is they cause the nearby protons to split, the signal to split. So if I have a hydrogen that is adjacent to one other hydrogen, the signal is going to be split into what's called a doublet. If a hydrogen is adjacent to 2 equivalent hydrogens, that signal is going to be a triplet. Okay, so it's called the N+1 rule. Number of peaks in a multiplet can give additional information about the structure of the molecule. The splitting of the peaks is caused by the neighboring carbon's hydrogen atoms. Protons in the same environment are said to be equivalent and behave as one proton. And then the splitting effect follows the N+1 rule. N is the number of hydrogen atoms attached to the carbon next door. N+1 is the number of peaks that are going to be seen in the cluster. So if we look at 1,1,2-tribromoethane, these 2 hydrogens are in one environment. This hydrogen is in the other. 1, 2, 3. They are within 3 bonds of each other. These 2 hydrogens are neighbored by 1 hydrogen. This 1 hydrogen is going to cause this signal to become a doublet. This hydrogen has these 2 protons within 3 bonds So this signal is going to be broken into a triplet. Here is what's meant by a doublet. You can see this one peak split into two, and then here's the triplet caused by these two neighboring hydrogens. Looking at 1,1-dichloroethane, I have this one chemically equivalent hydrogen, these three. The peak for these three has this as a neighboring, so I should see a doublet. Over here I do. This has three hydrogens neighboring, so this should be split into four, and it is. It's a quartet. Okay, we'll look at these in class, and that's the end of this screencast.